In this video, we are going to talk about combustion reactions. Now, before we talk about combustion reactions, we need to talk about the chemistry of fire. So, fire is self-sustaining and it is a chemical reaction. And through that process, the chemical reaction releases energy in the form of heat and light. So, it's kind of weird of thinking of energy, and there's all different types of energy. But the process of fire, or the chemical reaction of fire, it produces both heat and light energy. Now, arson is when a fire is deliberately set and it will destroy some sort of property or area. We have this fire triangle, and these are the three components that a chemical reaction that produces fire, it must have. So we must have oxygen. So remember, oxygen is a diatomic element and it doesn't exist as just O. It always exists as O2 and it is a gas at room temperature. There is a also heat, and then there has to be something to burn. Now, when we talk about fire and heat and energy in the form of light, we need to make sure that we're not confusing the term heat and temperature. So, heat is energy, and it is always transferred from hot objects to cold objects. We use the measurements of joules, which is given the symbol capital J, or calories, which is given the symbol lowercase c, cal. 1 calorie is equal to 4.184 joules. So you can use that conversion or that equality to convert between the two. A nutritional calorie is equal to 1 kcal or 1,000 lowercase c calories. And a nutritional calorie is a capital C calorie. That does not look like kcal. There we go. So heat is a transfer of energy in the form of heat. Temperature, on the other hand, is a measurement of that heat. It's a measurement of the kinetic energy, how they are moving between the particles or molecules within the chemical reaction. Thermal equilibrium is where the temperature of two different objects will become equal and remain constant when they come into contact with each other. So if you have a system that is in low temperature, which means your particles are moving pretty darn slowly, you have a system that is at high temperature and your molecules are moving very quickly. If you mix them together, then they will both eventually reach the same temperature. And that is thermal equilibrium. All right, now let's get into combustion reactions. And combustion reactions are a redox or burning reaction where oxygen gas is a reactant. Now, keep in mind that oxygen gas is O2. When a hydrocarbon undergoes combustion, the products are always carbon dioxide and water. Remember, a hydrocarbon is something that contains only hydrogen and carbon, nothing else. When you have a sudden explosion due to a buildup of fuel, and then that oxygen gets rushed in, that is known as a backdraft. And that can happen in a lot of structure fires because if you have an area where the oxygen has been consumed because of the burning, and all of a sudden you open a door or a rush of oxygen gets left or gets exposed to the area, all of a sudden there's more reactant for the fuel to burn. So you can get a huge smoke explosion, and it can be a really scary thing. When you're doing a combustion reaction, the color of the flame and the smoke is going to indicate how efficient a reaction is. If there's too much oxygen, if there's not enough oxygen. A lot of times, this yellow flame you see here is a result of having too much oxygen and not enough gas, if this is a propane stove. A lot of times, you can have water in your fuel sources, and that will cause this kind of white looking smoke. If you have really a lot of dense fuel that has a high burning temperature, then you can get this really dark cloud of smoke here. In Yakima Valley, we are unfortunately in an area where we get a lot of fires, especially in the summertime. And you can tell a lot about a fire based on the color of the smoke and how high the plume is. If you have smoke color that is lighter in color, it means that there's probably not a lot of fuel. It's burning through very fast fuel. And a lot of times those are our grass fires. And they start really fast, but then they burn really fast. And a lot of times they go out really fast. On the other hand, if you have a forest fire that's burning a lot of timber, that fuel can keep burning for a much longer time. And the smoke is going to be a lot darker, and those fires tend to last a lot longer. So here are the steps to writing or to balancing a combustion reaction. You want to write the unbalanced reaction and count all of the atoms, balance the carbons, balance the hydrogens, and then finally balance the oxygens. So let's look at an example. We want to look at the combustion of butane. So the first thing I'm going to do is write out my chemical equation. Since it says combustion, then I know that it is reacting with oxygen. Butane only contains carbon and hydrogen, so I know it is a hydrocarbon. And the combustion of a hydrocarbon always yields carbon dioxide and water. So now I can count all of my atoms. On my reactant side, I have 4 carbons, 10 hydrogens, and 2 oxygens. On my product side, I have 1 carbon, 2 hydrogens, and 3 oxygens. Notice I have 2 oxygens from my carbon dioxide, but then I have one more from my water. So check, we just did that first step. Now I want to balance the carbons. So that means I'm going to put a 4 in front of the carbon on my product side. And when I do that, it changes the number of carbon on my product side. So now I have 4 here, but it also changed the number of oxygens. So now I have a total of 9 oxygens. I have 4 carbon dioxides and 2 oxygens in each one of those, so that's going to give me a total of 8, plus the 1 oxygen from my water to give me a total of 9 oxygens on my product side. Step 2, check. Now I'm going to balance the hydrogen. So in order to balance the hydrogen, I have 10 on my reactant side, 2 on my product side. I'm going to put a 5 in front of my water. So now that changed my hydrogen count to 10, but it also affect my oxygen count. It also affected my oxygen to count. So now I have 8 oxygen from my CO2 plus 5 oxygen from my water to give me a total of 13 oxygen atoms. So I can put a 13 right here. Now my next step is to balance the oxygens. Whoops, for the hydrogen. When I go through and balance the oxygens, I notice that I have 2 oxygens on my reactant side and 13 on my product side. So this is where it gets a little funky because in order to balance this, I'm going to have to put 6.5 on my oxygen on my reactant side. And when I go through and balance my oxygens, I see I have 13 oxygens. So my chemical reaction is complete. However, it's really not a good thing to have a half a mole because when we're talking about the energy in chemical reactions, we generally talk about it in terms of 1 mole of the reaction. So you need to multiply all of the coefficients by 2 so that you can get whole numbers. And I can rewrite that equation. It's going to be 2 moles of butane reacts with 13 moles of oxygen to yield 8 moles of CO2 plus 10 moles of water. So this would be my final answer. Hydrocarbons are not the only thing that can undergo combustion. Metals and nonmetals can also undergo combustion, and the products are heat and light. Now, to get the chemical products, you're going to need to see how they combine. So let's look at an example of the combustion reaction for magnesium. So again, just like before, I'm going to write out my chemical reaction, get my reactants, and get my products. So we will have magnesium reacts with oxygen because remember, oxygen means combustion. And this is going to be a synthesis reaction because I have magnesium by itself, oxygen by itself, and they're going to combine to make magnesium oxide. Now, magnesium is a 2 plus ion, so it is going to be 2 plus. Oxide is a 2 minus ion, so it's going to be charge neutral as it's written. I don't have to add any coefficients. And then I can go through and balance my entire reaction. I have 2 oxygens on my reactant side, so I can put a 2 in front of my MgO. And when I did that, I made my magnesium not balanced, so I can put a 2 in front of the magnesium to make sure that it is balanced. Here is an example of magnesium burning. This is the magnesium ribbon, and the result of this is just pure light. And the leftover ash that develops is the magnesium oxide. Here are some practice problems for you to do. If you email me the answers, you can check to see if they are correct or not, but I really encourage you to do this because it will help you with your quiz.